theory, understanding the drug, whether it is well soluble or a very good, or the solubility is a rate limiting factor. There are various theories which are postulated by the scientists on drug dissolution. Your dissolution is termed as a process in which a solid substance is going to get solubilized in a given solvent. So there is basically a mass transfer taking place from the solid surface going into the liquid system. So there are various theories, which is called as diffusion theory model or film theory. Second is the Dankworth's model, or we say as a penetration or surface renewal theory. Then there is interfacial barrier model or a double barrier or limited solvation theory. Moving on to the first, the simplest and the most commonly used theory, diffusion layer model and or a film theory model. Here, the dissolution of the solid particles will take place in a liquid. They consider that there is no chemical forces is happening to carry out the dissolution of the solid particles into the liquid. So basically, two steps are said here. Here, what happens is as the solid comes in contact with the GI fluid or the film or a layer at a solid and liquid interface, which this theory says it should be a stagnant film or a diffusion layer, and this layer would contain the saturated amount of drug, and basically the drug coming from the core to the upper layer is rapid. Later on, there is a diffusion of this soluble solute from the stagnant layer to the bulk solution. Now, from this bulk solution coming back from the stagnant layer coming to this bulk solution is very slow, and so it is considered as a rate determining step for drug dissolution. Yes, with the help of this diagram, I would like to explain again. This is a solid tablet. Okay, once this tablet is ingested inside the body, it comes in contact with any GI fluid, maybe for example, take it as stomach also. What will happen is the drug from the core will start coming at the top and forms a saturated drug solution layer, which is given as a mesh, here shown as a mesh. So the drug coming from the core to this stagnant layer, which the theory says is very fast. Once this is a concentrated layer which is formed, then depending on the solubility of the drug in the GI fluid or in the water, the drug will get dissolved and come out. So this is a very slow process which takes place. So as per this theory, the theory says the layer which is formed at the top is a stagnant layer. The drug coming from the core to the top layer is a fast process, but the drug coming from the stagnant layer to the GI fluid is a rate determining step depending on the solubility of the drug. Am I clear till here?
Yes, ma'am.
Yes. So this is a stagnant layer through which the molecules are diffusing out to the bulk solution. Okay, and after it is in the solution state, again depending on the type of transport, passive or active, it is further taken through the GI to the blood. So here the equation, what we say, the rate of dissolution when the process is diffusion controlled, where you can see from this mesh the drug is going to come out into the system or into the GI fluid. And here they are considering no chemical reaction. Here basically is given by Noyes and Whitney's equation. Dissolution rate, which is the change in concentration of the drug with respect to time, is directly proportional to the dissolution rate constant, which we say it to be a straight line dependent on the concentration, is the first order, is directly proportional to the concentration of the drug which is present in this stagnant layer. Okay, which is said to be a maximum drug concentration, and the drug which is present in this GI fluid at any given time. Okay, so drug which is directly the concentration of the drug at a given time is proportional to how much of drug is present in the stagnant layer, which is a concentrated layer. So it will be always first minus the drug which is in the diluted form in the bulk solution, that is your GI fluids. This equation, as per Fick's second law of diffusion, Nernst and Bruners have incorporated the Fick's first law of diffusion and hence modified the noise and Whitney's equation, in which they have utilized, as per Fick's first law, which you had seen, the parameters like diffusion coefficient of the drug, the surface area of the dissolving solid, and the partition coefficient of the drug between for the basically considering the dissolution body fluids are aqueous, since the rapidly with which the drug dissolves depends on the partition coefficient, which is also dependent on the intrinsic dissolution rate of an individual drug. Then it is inversely proportional to the volume of the dissolution medium and the thickness of the stagnant layer. Am I clear?
Yes, ma'am.
Yes, ma'am.
Yes,
Okay, so the earlier Fick's law of diffusion jo hai, those parameters are incorporated into the noise and Whitney's equation so that you can include more parameters into it. Okay, so if I consider a diffusion coefficient, if the diffusion coefficient value is high, the drug can faster dissolve. So what easily the GI fluid can enter inside and the drug can diffuse outside. Diffusion can decrease if the viscosity goes on increasing. Then there is surface area. If the surface area is more area is exposed for wetting of the particles, and so the faster dissolution will take place. So that is why researchers like us basically work on reducing the particle size by preparing nanos and microparticles. Then the partition coefficient, again, if the value is high, okay, we can say now this is with respect to solubility parameter. So if the coefficient is high, that means the drug is more lipophilic and it is more readily dissolved into this GI fluids or aqueous fluids. Then the concentration gradient, we know that in the stagnant layer, there would be more amount of drug, and in the bulk solution, there would be less amount of drug. Okay, that means the drug can diffuse from the higher concentration to the lower concentration. Then the thickness is very important of this layer. If the thickness goes on increasing, the rate goes on decreasing. Okay, so now this undergoes, the equation shows that it undergoes first order kinetics. Okay, and the driving force, as I told you, the stagnant layer has more amount of drug, which acts as a driving force for the movement of drug from the stagnant layer to the bulk layer. So under such situation, dissolution is said to be under non-sink condition. This is true in case of in vitro dissolution in a limited dissolution medium. What happens is, if I'm carrying out dissolution study in vitro and if I don't replace, okay, with the fresh media, when I remove an aliquot for analysis, the medium becomes limited for the solubility of the drug, and hence the solubility of the drug can be inhibited or stopped because it is already saturated. So dissolution in such a conditions will come down, and so because the concentration of the drug has saturated the bulk solution and now no more drug will go into it, so the dissolution will actually stop. This is as per theory, but if we see it inside our body, the dissolution is always rapid, because as the drug dissolves, simultaneously it will go for absorption and absorbed drug will go into the system. So what happens is the bulk will never be concentrated, or we say saturated. Okay, so the movement, as I explained yesterday also, the movement simultaneously is taking place in the body. So nowhere in the body the drug absorption or drug dissolution will stop. So it is a dynamic process. So that is why in our labs also what we do is we remove an aliquot and we replace the fresh medium back of the same equal volume into the system. So under in vivo condition, there is no concentration built up in the bulk of the solution, and so there is no retarding effect on the dissolution rate of the drug, because the stagnant layer will always be concentrated in the bulk solution. And so in this way, the sink conditions are maintained. Under sink condition, if the volume and the surface area, if we keep constant, as per this theory, they are saying you are taking a constant volume for analysis, for carrying out the test, and the surface area is also remaining stagnant, so there is no change in the surface area of the drug, then the equation can be given as dC by dt is directly proportional to the absorption constant, that is K, which can be also written as dC equal to K dt. Here the concentration of the dissolved drug with respect to time is being plotted. So the dissolution rate is constant. If we say under sink conditions, you get a constant line, straight line, which follows a zero order kinetics and gives you a linear product. But if I follow this first order, what happens? Initially, the drug is going to get solubilized in the bulk solution. But if the bulk solution is not replaced or the bulk solution is not replenished, then there is going to be a saturation, which could give you a curvy linear plot. Am I clear till here?
Yes, ma'am.
Yes, ma'am.
So to have a better understanding, a good in vitro and in vivo dissolution rate correlation, we have to approach to the sink condition. We have to follow the sink condition, which we can do by you reconstitute the fresh solvent. When you take an aliquot, which is a solid rich aliquot, should be replaced with the fresh media of the same volume back at the specified time. Then we can also work on, if we find out that you are getting a dissolution rate or absorbance which is constant, which can give us an idea that the medium is insufficient for dissolving the drug. So if I'm working with something 500 ml, I need to improve or increase the dissolution medium for the next study so that I can have a proper flow of the release pattern. Then we can also do one thing, that you can take up the drug, okay? Then what we do is we carry out partitioning between, like octanol water system use karte hain, jo analysis mein hum log use karte hain. So you have a aqueous layer, you have an organic layer, you put your aliquot into it and you shake it. So drug ka solubility jisme bhi aata hai, that we need to separate out to get maximum where the drug has actually gone. So that can be either in the organic layer or in the aqueous layer. So aqueous layer, basically we are not, if it is partitioning, we always tend to see that the drug is not soluble in aqueous layer. The drug will go into the organic phase. And that phase can be utilized for analysis of the drug. Then we can, in your dissolution media, to improve the solubility of drug, we add around 0.2% or twin 80 or twin 20, which will increase the solubility of the drug inside the system. Even for, if we see, if I'm carrying out a dissolution study for dermal, for that, the reported dissolution medium as per pharmacopoeia is octanol. We can go for octanol and water system for improving the solubility of the dosage form, so that you can get good absorption, because in our body, it is mimicking it. Similarly, in the body, we have surfactants also. So twin 80 can also be added as an external into this dissolution medium. Sometimes we can add alcohol, but then whenever we are using medium apart from what is mentioned in the pharmacopoeia, we need to justify it. Why are we using this solvent? Because we are using dissolution so that we can mimic the activity which will happen inside our body. So outside contents needs to be justified. Then we can also have adsorbents added so that we can have more access to the drug.